Today we are going to do chapter 4.1, function of two variables. Now that means, for example, f of x and y. Normally we do just x, but now we have two things in there instead of one. Now the function of two variables, of course, has a domain that's in 2D. That is, before we have a domain that's just on the number line, then now we have the domain and include both the x and the y axis. But however, the function of two variables still has only one result. That is, we take two numbers and then come up with one number. Such as, and in graphics, you can think of it like this. See, your domain is some area, 2D area, whereas the range is a 1D area. Now, as an example, let's look at example 4.1, all right, where we have, what is that? A couple of functions. What is the domain and range? Now, when you look at part A, then it's just some regular thing, right? There's no catch in there. So the domain is the whole real plane, and the range is the whole real number, period. And then part B, here's the catch, right? Here's a square root, and with the square root, you can't have anything that's less than 0. So which means the domain has a catch. That is, we have 9 minus x squared minus y squared. Now what happens with this thing? We need this thing, the thing inside, to be bigger than 0. So 9 minus x squared minus y squared has to be bigger than 0, which means if you write it this way, put it the other side, is x squared plus y squared minus 9 has to be less than 0. What is that? That's a circle of radius 3. Okay, and so this is 3. All right, and then it has to be less than that, so the domain is all the circle on the inside. Now the range, where is this going? Well, if this thing is, if it's coming from x and y, has to be less than 3. That's the domain. Okay, then I think we write it as yeah. Well, how you write it is. Never mind how you write it. The point is the domain is in here. Well, actually, this is how you write it. Okay, here's the domain. Now the range is, well, if x and y is restricted to be inside the circle, where does this value go to? Well, at the most, it will go to 0, right? Because if x and y equal to 3 each, so can x and y equal, wait a second. Sorry, x and y cannot both be 3. It's just, they fit this equation. So when x and y are 0, however, then this thing will become 0 be 3, right? And that would be, and anything else, then this thing is going to be less than 3. So the range is somewhere between 0 and 3. That's the range, okay? 0 to 3 is the range. And you write it officially some other way, but that's the idea. And that would be, that covers example 1. Now let's flip the page. Next, let's look at page 337. Graphing this thing, how would you graph it? Let's just, to graph this thing, let's plug it into some calculator and graph it. And then if you do, it will come up with something like this. I haven't tried the calculator yet, but this is definitely, for example, this equation is, this is a couple pages later where we have z. Oh, that's the same thing we just did, right? And that's a circle. And then if you have a z coordinate, then it becomes, well, a sphere, basically. Is if you have to, by the time you're done with the math, then you realize it's the equation of some sphere. Yeah, and that's about that. And then the other thing that's being graphed in this thing after you type it into the 3D calculator, which I'm sure is able to do, although I haven't tried it yet. But and the point is, then you type it in, out comes this thing. Now, when you graph stuff on the calculator, you still should have an idea yourself, if possible, what this thing looks like. For example, it's x squared. This graph is x squared plus y squared. Then you know it's some kind of parabola, because y equal to x squared is a parabola, right? And then z equals y squared is some other parabola. It says parabola in both dimensions. And this is an easy example of how you might be able to visualize what this thing looked like. If the equation is too complicated, then you wouldn't be able to see it so quickly necessarily. But if it's easy enough to see, then you should be able to visualize it yourself before plotting it in. That way you know that the calculator isn't pulling the wool over your eyes and plot some garbage that you don't recognize. That can happen, for example, if you typed in the wrong thing, right? And then your graph is completely off. And anyway, so let's see. Yeah, let's turn the page, okay? We'll skip example 4.3 because that does zip. And let's go next to page 341, where we are looking at something called a level curve. What's a level curve? A level curve is some trick that's used before graphics calculators are invented. Before 3D graphics calculators are invented, to draw lines on a map to indicate the even height. For example, and this is taught in geography, okay? For example, if you look at some graph that looks like that, you see a bunch of lines. Now each line indicates elevation. Yeah. So, and each line is different from the other line by the same amount. Maybe, say, for example, each line is, 10 feet or 10 meters apart, something like that. So that if you see lines farther apart, then you know the difference in height is not that much. Whereas if you see the lines all packed together, that means the height is increasing rapidly right there. So you can sort of imagine it. And so this is the graph of that object over there. See? It looks pretty neat. I wonder what that is. Whatever. I guess it's called Devil's Tower. Is this a devil? Well, whatever. The point is, so those are equal height lines. Okay, they are called a level curve. Fine. And the purpose is just so that you can visualize it if you don't have a 3D calculator, which nowadays we do. Right? If you can watch my video, you most likely has access to the 3D calculator. But if you don't, then these lines can come in handy. But anyway, so you graph this thing. The way to do these 3D calculators is you just set the function equal to whatever number it needs to be and then graph that line, which is not easy by hand. Okay, so hopefully you don't have to do that by hand or by anything else. But anyway, that is how things were done. You just equal to 2, you draw the line somehow, and then it equals to 3, and then you draw it again, and you keep doing that until you have a ton of lines. And then that would be example 4.4. Now that's yeah. Should you do example 4.4? Maybe. I'll think about that later. Now, so moving on, and I think I wrote it down maybe. Maybe all the examples, but I will. I'm using new equipment today. It's hopefully to get rid of that clicking sound in my video. So my stuff isn't all on this new computer. Anyway, let's see. I'm not sure I want you to do a contour map. It sounds like, well, maybe do it, but just type it into the graphics calculator and take a look at that thing, and that should be good enough for anybody. And yeah. And don't even bother with, the contour lines, but know what they are, okay? You just have to set them to set numbers, increasing by set amounts, and then draw the lines, and which helps you visualize this object. For example, this example, you came up with a bunch of contour lines, but that's not near as good as actually drawing the thing in 3D now, is it? So anyway, let's move on. There's something next. The book wants to mention something called a vertical trace. That might come in handy later. A vertical trace means you set something, set the equation or part of the equation into a fixed number, and then figure out what that plane is. Like, for example, in in the equation, here's the example 4.5, right? You have equation z equals sine x cosine y, and they want you to set, for example, fix x at minus pi over 4. If you plug that in, it becomes c equal to some number times cosine y, and that is a plane, right? It's a cy plane or something. Is it a cy plane? I don't know, let me think. Sorry, I said that wrong. It is not the CY plane, it's the vertical trace. That is the intersection of the 3D object with the plane that's called x equal to minus pi over 4. And for example, like this. See, here's a chart, here's the plane, and then there's the trace. In other words, this is just a line, right? A graph of a function, of a 2D function. And it basically what happens is you take the plane and cut it across the 3D surface, and then it traces a line if you do that. And what does that trace do? It might give you an idea of what this thing looks like. Again, that's because, why are we doing that? Because and that this is leftover tricks from back when Desmos 3D wasn't invented. Okay, nowadays we don't have to do that, and but it still should be mentioned just so that you know how people in the old days without technology used to suffer, right? And anyway, so in general, let's now look at page 346, a couple pages later. Let's look at this thing right here. Okay, this is some random 3D graph, and that is the function of two variables, x squared sine y, whatever. So you notice that the graph is quite folded, and the one next to it is even more folded, right? And so, I mean, by folded, I mean lots of wrinkles. However, remember that for any 2D function, it's still a function. That is, in a 1D function, and if you draw anything like maybe sine or cosine or something like that, you know, it goes on. And but there is one condition of the 1D function is this thing can't turn clear around, because if it does, then you have the function will end up with two answers, two y's, and that's not possible. Okay, that's missed the definition of function. That is, it can't ever fold back. It has to keep going. It might go to infinity, whatever, but it cannot actually go back and double back. So, and for the 2D function, the principle is the same. Your graph might wrinkle a lot, but it cannot possibly fold back. Okay, that's not a function. I mean, there are things that 3D objects that fold back, of course, like the ellipsoid that we saw earlier. Is ellipse, well, whatever, you know, the egg-shaped thing. But all the ball, okay, they have two results, but those are not functions. A function, even if it has two variables, still has to observe the rule that it has one result, okay, which means it cannot spit out two of them, and therefore it cannot fold back. And then next we will consider function with three variables. And now, because before we did c equals f(x,y), now we'll add something else to it. And what do we call this? Okay, let's call it, for now, your book calls it something like f of x, y, z equal to what? Whatever. Okay, the point is, we'll add another variables in here. Okay, so now we have three variables, and three variables is not different than two variables, except that now you got three things to deal with, so you have to do 3 times the work. But everything else is basically the same. So then you can find the domain of this thing. Let's look at example 4.6, where you have a couple of things to look for domain. Yeah, please do this example as part of your homework, I guess. You just to find the domain, you basically just make sure that the denominator is not 0. And then you're good, which, yeah, anyway, so do that. And which is just the same thing you've done many times, right? Figure out when something isn't 0. And so let's go to the next page, page 348, where we have a level surface. So instead of the level plane, now we have something called a level surface, which again means that you have the function set as a constant and then solve it and see what it looks like. So if you did that, look at example 4.7. And so you have some random function here, okay, with 3 variables. And if you were to plot the level surface, then see if you let the function equal to 1, okay, and 2 and 3 and so on, which is fine. Then you come out with 3 surfaces. But what does that tell you really? Not a whole lot, because by then what happens is with the function in 2 variables, we can represent it with a 3-dimensional object. But the function with 3 variables, we need a 4-dimensional object to represent it. But we as humans are not able to envision to represent the 4D, right? So then they use this to give you an idea, which I don't think that's really necessary, because and what does that tell you? It doesn't tell you a whole lot. The function doesn't look anything like this. Just like in 2D, the trace line is not like the 3D object at all. It's just a bunch of lines. And similarly, in 3D, the trace surface doesn't tell you a whole lot. And what's more, okay, so they stopped here. So that's what happens when you have a function of 3 variables. Well, my question is, what happens when you have a function of 4 variables? Now what are you going to do? Are you going to do a trace what? There's nothing to trace. Okay, by then the trace is going to be in 4D as well or something, and then you're out of luck. So that's what I mean by the trace is not necessary really, because we might or might not need to visualize exactly what this thing looked like, but whether you visualize or not, you're still going to do whatever you're supposed to do there. For example, you can evaluate a function with, say, 5 variables. If they ask you what is the function at this value, you can totally do it. You don't have to visualize it to do that, right? You just plug it in. It doesn't matter how many variables there are. When you evaluate it, you plug it in. And the same as when you take derivatives of it, which we haven't done yet, we will do it later. When you integrate it or whatever else that you can think of to do with it, you don't have to most of the time you don't have to visualize it, or if you do have to visualize it, you only have to visualize a small part of it to make the whole thing come out. So having said that we have come to the end of this section. So let's talk about homework. So for homework, please do let's see, well, first for the examples, please do examples 4.5, 6, and 7. Let's see down here. And yeah, okay, that's pretty good. And then for homework, when I say do the examples, I just mean like, look at them, maybe type something into the graphics 3D and see it comes out, that sort of thing. And well, basically just remember what or know what those things are: levels, traces, that's whatever. And then for the homework, please do problems 7, 11, 21, 31, 37, 41, 51, and 57 on page 350. This is just the first part of a very long chapter, and this part may sound like easy and straightforward, and it is. It just is a repeat of what we learned before, basically, except that now it's extended to the 2 dimensions, but otherwise nothing's different. So, but things will get more interesting later. So don't worry about that. Okay, and and with that, I believe that's the end of this section. But before I go, I want to mention that whenever I have a short section, I like to make a literature recommendation, because I'm really into literature, and which by that I count even movies and TV, all those things, okay, ways that people represent themselves in novels or stories. The one book I like to recommend, if you haven't read it already, is Pride and Prejudice by Jane Austen. It's a fantastic book, extremely funny, and to the guys who are watching, it is not a romance novel. Okay, not that there's anything wrong with romance novels, but I want to be clear on this: is that Pride and Prejudice is not a romance novel, despite the fact that it does have a romance love story embedded, but that isn't the main focus. The Pride and Prejudice is a fantastic story. Jane Austen wrote it when she was, I think, 19 years old or something like that, and it's amazing. All right, so if you have read it long ago, please consider reading it again. It doesn't hurt to read that thing again, many times. I read it all the time. And well, when I say all the time, I mean every so often I would read some of it, because it always cracks me up to hear all the characters and all those things. So if you haven't read Jane Austen for a while or never, be sure to read Pride and Prejudice. be sure to read Pride and Prejudice in your spare time, and it's fantastic. And if you don't speak, if English isn't your first language, there's nothing wrong with reading it in your own language as well, if you can find it. Yeah, well, anyway, so that's all I have to say about that.